Since we are young children, we are told different kinds of stories. Some of these stories have to do with the way we are born. Other stories have to do with the origin of the things that surround us. Today, I will tell you two stories. One of them will be about the gas giant planet Jupiter, and the other will be about myself. It was the American poet Muriel Rukeyser who once said that the universe is made of stories and not of atoms. Interesting. What do you think? Well, hopefully at the end of my presentation, you will have your own opinion on this matter. This is Jupiter. We have been studying Jupiter since hundreds of years. We know that Jupiter has, for example, a giant red spot, a huge storm in the surface of Jupiter, much larger than the size of the Earth. We know that there are zonal winds, winds that go in opposite directions and create the turbulence we see in the upper atmosphere of Jupiter. We can observe this with huge telescopes, like the Hubble Space Telescope, but we can also do it from our own backyard, like these folks who just a couple of weeks ago took these images of Jupiter, also Saturn, if you can spot it right there, and put it on Twitter. So people are fascinated about Jupiter for different reasons. And not only Jupiter, but also the moons, as you can see right there. These are satellites that orbit Jupiter in a similar way that the moon orbits the Earth. Now, how did I get involved in Jupiter? Let me tell you, it was not an easy way. I did not begin looking at the sky, but much rather, I began looking at what was below my feet. Since I was a young fellow, I was interested in knowing what was at the center of the Earth. So, as many of you maybe have done, when I went to the beach, I would make holes, trying to know what was in there. This is perhaps my first attempt in my journey to the center of the Earth. Of course, it didn't go well, but later, I would learn that using physics and math, you can learn about things that are inside of the Earth and also inside of other planets. So let's go to the beginning of my own journey. This is Chiloé Island. It is an island off the coast of Chile, in a region in South America known as Patagonia. This is a special place. It has its own culture, its own traditions, its own architecture. For example, here you have a picture of some of the churches that you can find in many of the towns in Chiloé Island. They have different colors, different shapes, and they have different sizes as well. In terms of traditions, we have some traditions that might seem a little bit odd for a foreigner. For example, normal people, when you move from one place to the other, you want to live in a different place. What you do is you take your personal belongings, sometimes you take your furniture with you, and you move it to the other place. In Chiloé, you not only do that, but you take your own house with you. Like the house you see there floating on water, that's been taken from one island to the other within the archipelago of Chiloé. In addition to that, we have special traditions in relation to food. Like those folks right there that you can see in the image. They are cooking what is known as a curanto. In a curanto, you make a hole in the ground. At the bottom, you put hot, large stones that you need to preheat on the side. On top of the stones, you put your meal, which can be seafood, potatoes, even meat. You cover that with leaves and you let it there cook for a couple of hours. That is a dish that can feed over 20 people. So in this island is where I went to high school. I went to a public high school with certain emphasis in physics and math. But more than the classes I took, what was really important was this professor that I had, Alejandro Guajardo. He was the first person who taught me that I could use simple physics, the laws of Newton, for example, to predict the motion of the planets when they go around a star, or the motion of the moon when it goes around Earth. When I graduated from high school, I had to move to a different city because there was no university in Chiloé. I went to Santiago, the capital city of Chile, to study engineering. I studied civil engineering and earthquake engineering. I learned how to build things and also to make them resistant to earthquakes. By the way, during the time I was studying, going through college, there were 3 major earthquakes that shook Chile. Not only the population was, shaken by these movements, my own scientific interests were shaken as well. I began to think on my first interest on understanding the Earth. I began to think that I wanted to learn how Earth works, how earthquakes work, rather than to build things. So that's when I decided to come to Caltech in 2017. I came here to study Earth. I obtained a master's in geophysics, and I am still working on my PhD in planetary science. You might think that this journey goes into different directions, but there is something in common to all the things I'm doing. If you take the locations of the places where I have lived, and you draw a line going across them, as my friends tell me, you can predict where I will be in the future, and that is somewhere in the state of Alaska. But let's go back to Jupiter, the largest planet in the solar system. Jupiter, together with Saturn, are both a kind of planet that we know as the gas giant planet. They are made mostly of the elements hydrogen and helium. In addition to these two, we have Uranus and Neptune. These are also giant planets, but we call them ice giant planets. When we say the word ice, what we really mean is molecules like ammonia, methane, water, and carbon dioxide. In addition to these 4 giant planets, we have other 4 inner planets, the terrestrial planets, among which we have the Earth. These are the terrestrial planets. These are planets which are mainly made of rocks, on top of which you might or may not have an atmosphere. When we study planets, and when we study Jupiter in particular, we want to learn how to form these planets. We want to learn what they are made of. Not only these 8, but also these other thousands of planets that we now begin to observe outside of the solar system. These planets orbit other stars. We call them exoplanets. Some of these exoplanets are similar to Jupiter, others are similar to Uranus and Neptune, and others are similar to Earth. In fact, there is another kind of planet that is not similar to anything we have in the solar system. In any event, when we look at Jupiter, and when we try to understand the story of Jupiter, we're trying to come up with a story to understand the formation of all these planets. Jupiter is the largest planet of the solar system. When we look at Jupiter, we are looking at the main events that produce the solar system as we know it. And we can use that information to understand all these other thousands of planets. Now, what is that story about the formation of planets? This is a fascinating and exciting story that I would like to share with you today. These are the main steps of planet formation. There are many other details that we will not cover here, but these are the main stages. At the beginning, when you didn't have any kind of planet or star, you begin with a giant nebula of gas and dust. A nebula is like a cloud. In this cloud, in this nebula, gravitational forces begin to create pockets of higher density mass. These pockets of higher density mass grow until producing something that we know as a protostar. Around a protostar, we observe protoplanetary disks. From this structure is where we create planets. And the first kind of planet we produce are the terrestrial planets. In the protoplanetary disk, we still have dust and gas. The terrestrial planets come from the agglomeration of the dust in the protoplanetary disk. Take a parcel or a particle of dust. Now take another one. They eventually might collide, merge to form a larger particle of dust. If you take that process and you repeated it thousands of times, you get to form things of the size of Earth or Venus or all the terrestrial planets. you can form things even larger than that. And those things can become, perhaps, the core of the giant planets. Now, for the giant planets, you require an extra step. We have taken care of the dust in the protoplanetary disk, but we still have a lot of gas. Actually, the largest amount of mass in the protoplanetary disk is gas. Now, we have these cores, these objects of rocky material. The gravity of these objects eventually will attract the gas around and create what we know as Jupiter, Saturn, Uranus, and Neptune. This is a general story of planet formation, but we want to know the details of this. How in detail do you form the planets? And to do so, you need to know the details of what the planets look like in the inside. When we look at Earth, our picture is pretty clear. We know that we have a core, and in the core there is a solid inner core and a liquid outer core. On top of that, we have the mantle, and on top of that, we have the crust, where we live in. Now, when we look at Jupiter, and we try to reproduce something like that, a layered planet, some layers are more clear than others. We do know that there is a molecular hydrogen layer, and below that there is a metallic hydrogen layer. But when we think about the core of Jupiter, we have a lot of questions yet. We don't really know exactly what the core of Jupiter looks like. That is the object of my research. I am trying to understand what kind of core does Jupiter have. And the options that we have are a compact core or maybe a dilute core. In a compact core, you might think about this as a cloud, and at the center of the cloud, you have a solid piece of something that is maybe charcoal, okay? It's just an example. It doesn't need to be charcoal, but it's something that is solid. Whereas in the dilute core, you have the same cloud, but instead of charcoal, you have smoke. It is the same carbon, but in a different shape. It is diluted in the cloud, so there is no solid thing and compact element. How do we learn about these things? Well, telescopes are not enough. We need to pierce the clouds. And to do that, we need to get there, actually. And to get there means to send spacecraft. We go there sending spacecraft, exploring planets. We have been doing this for decades already. You might maybe have heard of Voyager, or Galileo, or Cassini and the flybys of Cassini around Saturn. Today, I want to talk about particularly the Juno mission. The Juno mission has been collecting data on Jupiter since 2013 or 2016 and continues to collect data up to this day. The objectives of the Juno mission are the characterization of the interior of Jupiter. And we can do that in three objectives. The first objective is to know more about the atmosphere of Jupiter. We want to learn things, for example, what is the distribution of water in the upper atmosphere of Jupiter? What is the distribution of ammonia? We also want to know things about the magnetic field of Jupiter. We are measuring the magnetic field of Jupiter using Juno. As Earth has, Jupiter also has a magnetic field. And learning about the magnetic field as measured in the surface can tell us how that magnetic field is produced in the interior of a planet. Now there's a third element, that is the gravitational field of a planet, that tells us about the distribution of mass inside of a planet, and that is where I work on. My research is related to the distribution of mass and the gravitational field of Jupiter. Now let's take a brief pause. We have talked about Jupiter, we have talked about the formation of planets, and we have said a few things about space missions and spacecraft. Now, I want you to take all those things that we have already covered and think about the journey I promised, because I promised you a journey to the center of Jupiter, and that is what we are going to do right now. Here you are, the upper atmosphere of Jupiter. Again, you can see the solar winds, you can see the giant red spot. Just below the upper atmosphere, you have the molecular hydrogen layer. Here, hydrogen binds together, forming a molecule of two atoms. Most of this layer, as is also the case for the rest of Jupiter, is made of hydrogen. Hydrogen is the most abundant element inside of Jupiter. But in addition to hydrogen, you also have helium. And helium is dissolved in the hydrogen. It is like when you have a cup of water and you put a little bit of sugar on top and you mix it and the sugar disappears. It is still there, but it's dissolved in the water. The same thing happens to helium inside of hydrogen. Now, in 1995, we had the Galileo probe crashing against Jupiter. We sent this probe to pierce the clouds of Jupiter and measure the composition of this layer. And we found something really surprising. We observed that the abundance of helium in this layer was much lower than what we were expecting. And what we were expecting to see the same amount of helium that we see when we look at the sun. Ultimately, these two objects came from the same nebula. Both Jupiter and the sun were made from the same nebula. They should have the same amount of helium. This puzzle, solving this puzzle, allowed us to learn something new about Jupiter, and that is that helium rains down in Jupiter. And the reason for this is related to the concept of solubility. Hydrogen has a maximum capacity to dissolve helium. If you put more helium than the capacity of hydrogen to dissolve it, the helium will rain down. Helium is ultimately heavier than hydrogen. So if they cannot mix together, the molecules of helium, droplets actually, will rain down until they can be assimilated again and dissolved at a greater depth. So that is what is happening in Jupiter. For that, I have a demonstration. So to understand how helium rains inside of Jupiter, we will use a small experiment with the solubility of water. Here I have a cup of tap water, and here I have a bowl full of sugar. If we take a small spoon of sugar and put it into the water and stir it, all the sugar crystals eventually will break, and the water will entirely dissolve the sugar. We might say now that the water has dissolved the sugar. This is the same thing that happens with hydrogen and helium when both elements are mixed together. In the case of Jupiter, hydrogen dissolves helium. As you can see, there are no remaining crystals of sugar. Now, take the extreme example where I pour a bunch of sugar inside of the water. Don't do this at home. Okay, that's enough. We stir it. In this situation, it doesn't matter how much we stir. We have gone over the capacity of water to dissolve the sugar. And this is exactly what happens also when you have too much helium in Jupiter. What will happen later is that the crystals that cannot be dissolved in the water will precipitate to the bottom of the glass. They will form, in this case, a crust of sugar. Well, that is what happens with helium in Jupiter. When helium cannot be dissolved by hydrogen, it rains down and goes down onto another depth inside of Jupiter where helium can be again dissolved. Below the helium rain layer, we encounter the metallic hydrogen layer and helium. Now we are deeper inside of a planet. The pressure is crushing us. The temperature is so high that the electrons that are usually bound to the hydrogen atom are ripped off, and they can now move freely in a sea of electrons. This is what we know as a metal. Now hydrogen can conduct electricity because the electrons move freely in this region. This layer not only can conduct electricity, but it's also a fluid. It can flow, it can move. So if you have a current there, you can move this layer together with conducting electricity. These two things, we believe, are necessary to produce a magnetic field. In this layer, the metallic hydrogen and helium layer, is where Jupiter produces a magnetic field that we are measuring with Juno. Now we get to the most important part at least for me. This is very close to the center of Jupiter. We're approaching the core. But here, unfortunately, things get less clear. We don't know all the answers. For example, as I said before, we don't know if the core is yet a compact core or a dilute core. We don't know exactly what the size of the core is, actually. And we are using Juno to answer some of these questions. The way we do this is tracking the position of Juno. Juno is an orbiter. Juno is going around Jupiter in a set of different orbits, and every time Juno passes close to Jupiter, we measure the velocity of Juno. The way we do this is using the Doppler shift effect. You might have experienced this in your normal life when you hear the noise of an ambulance. When you are in front of the ambulance and the ambulance is approaching you, you might hear a high-pitched noise. That means that the noise is high frequency. Now, if you are behind the ambulance, you should hear some low-pitched noise. That means low frequency. We do the same thing with radio waves that we send to Juno and that Juno sends us back. We measure the frequency of that wave, and we can tell whether Juno is getting closer to us or farther away. In fact, we can tell the velocity of the spacecraft. And now with the velocity of the spacecraft, we can use that information together with Newton's second law to infer the mass distribution of the planet. I will give you an example to illustrate this concept. Think about Jupiter as if all the mass were concentrated in a single dot. It's a single point. Now, if Juno goes around that single point, it will move with certain velocity. Now think of an alternative case. Jupiter is now following the shape of Mickey Mouse. It is the same amount of mass, but distributed in a different way. Juno, when it orbits Mickey Mouse, will follow a different velocity. Now we can use the velocity to infer what the distribution in Jupiter looks like. And answer, again, this question. From the formation of planets, did Jupiter get a compact core or a dilute core? Juno suggests that it seems that Jupiter has a dilute core. But this is not the end of the story. We have more questions because now we need to figure out why does Jupiter have a dilute core? How do you get to form a dilute core? From our basic understanding of planet formation, Jupiter should have something more like a compact core. That is the way you can attract the gas in the protoplanetary disk. So these questions are things we're trying to figure out right now at the same time that Juno collects more data. Before ending, I want to go back to the quote I gave you at the beginning. The universe is made of stories and not of atoms. What do you think now? I just show you that we scientists collect data all the time. We then make stories to understand that data. Sometimes that data changes the stories that we previously had. So we are giving shape to our understanding of the universe, creating more and more stories. In addition to that, I showed you a different kind of story, a story that has to do with people, with decisions that we make for our lives. Hopefully, these two stories will inform you, will allow you to decide what kind of story do you want to live? What kind of story do you want to create for yourself? And that is the end of our journey. I leave you a few resources here if you want to learn more about exoplanets, or if you want to learn more about the Juno mission, or if you are interested in my own journey. Thank you.
Thank you for attending today's Science Journey presentation. Here at Caltech, we thank Mitch Aiken and Kitty Cahalan of the Center for Teaching, Learning, and Outreach, as well as Mary Herrera and Kara Steeman from the Office of Public Programming, and the teams from Academic Media Technologies and Event Productions. And special thanks to Robin Javier and Brian Brophy. Additionally, we thank the Caltech Employees Federal Credit Union, the Friends of Beckman Auditorium, and our many sponsors who make these programs possible. We look forward to you joining us again for future science lectures and performing arts events. Learn more by visiting events.caltech.edu.